Okay then, so in the same way um, that we looked at um, the difference that was made by having a sample that had a different length and how we dealt with that by um, instead of measuring change in length, measuring this quantity strain, which is the change in length divided by the original length. And we found that using strain, it didn't matter what length the sample was, everything would come out in this calculation here, where we divided by the original length, such that a greater change in length due to the fact that there was a greater original length meant that when you divided the first by the second, the change in length by the original length, then that brought this back in line with a common quantity between the two samples. We've still got load P, a load P on this axis here. And if we look at that quantity now, imagine if we have a sample this time which is the same length as our original sample, but this time it has a greater diameter. Okay? And that greater diameter is such that this sample has an area A1, A subscript 1, and this sample has a larger area where A2 is greater than A1. Okay, so the area of this sample is greater than this sample, the first sample, the original sample that we had. We're still going to have the same force that we apply, and that force is still going to be the P that we had over here in this sample. And the original length of this sample is going to be still the same. So we're keeping everything the same. All we've changed this time is the fact that we've got a sample with a larger diameter. So the area 2 is greater than area 1, area subscript 1, A subscript 1. Okay? And in a similar fashion, we're going to say that A2 is greater than A1 such that A2 is equal to twice A1, so 2 times A1. Okay? We've done a similar thing with this P variable here. Okay? If you remember how we dealt with the fact that now we have differing samples and we can reasonably expect that in actual fact this strain, the change in length divided by the original length, is likely to be less than in this situation, so delta L2 is likely to be less than delta L1 because we've got more material to stretch using this same force. Okay? So we find if we do the experiments, and you will do the experiments in the labs, that those changes in length are different for a different area, and that is proportional, or in other words, as we described before, the relationship between those two is linear. Okay, so if we double the area, we will halve the strain under the same load for the same for all of the conditions remaining the same material, same temperatures, etc. So we now need to have a way of bringing that into line such that we can compare any sample with any other sample, just despite the fact that some of the variables might be different. In this instance here, we looked at the fact that the difference in original length was a factor in our outcome. Here we need to cater for the fact that the difference in our original area is a factor in the outcome. Okay, so if we now consider this force, which is what we've measured on this axis here and what we've changed in order to give us changes in the change in length. We now need to factor into the equation the situation with regard to the area. So if we now do a similar thing to what we did here and divide by the original area, so A1, okay, we end up with a delta L1. So that gives rise to a strain of delta L1. Okay. If we now look at this situation and we have P divided by the new area A2, we now get a change in length delta L2. And we found by the experiments that we've done in the lab that for an A2 which is greater than A1, to the extent that A2 is twice A1, we found that delta L1, which is this strain here, or this change in length I should say, is twice the second. So it's greater than delta L2, and it's greater to the extent that at delta L1, this strain, or the change in length per given length, and because we've got a given length which is common to both of them, we can talk about it, it's just the change in length, but strictly speaking, if you remember, if we call it the strain, then we don't need to worry about the original length. So delta L1, it turns out, is twice delta L2. So in that situation where delta L1 is twice delta L2, for a situation where A2 is equal to twice A1, we can now look at these outcomes by measuring, or this outcome here, in terms of this new quantity, which we're going to call the force divided by the area. And we find that if we substitute for A1 for A2 in here, we find that P over A2, which is the same as P over twice A1, so P over 2 times A1. For that situation, we give rise to a change in length, delta L2, where delta L2 is half of L1, or delta L1 is twice delta L2. Okay. So that gives rise to 1 over 2 delta L1. Okay. So we've halved this value here, and we've halved this value here. So we can see then that, similar to what we did for strain, we now have this new quantity, which we're going to call stress, and we'll give it the Greek symbol sigma. The Greek symbol sigma is just the Greek letter of the alphabet that we are going to, by convention, refer to our stress by. And we see that if we measure, instead of measuring force, we measure stress, which is the force divided by the area. It doesn't matter what this area is. For the same stress, we will always get a strain, the same strain for any given stress. So that the force may change. We may need, in order to get the same strain in order to make this twice as big, we may need to make this force twice as big. But again, 2p over a subscript 2, a subscript 2 is twice the size of a subscript 1. So although we've got 2p, we've also divided that now to get our strain, to get our stress by 2a1, such that that is reduced again to p, the p that we had here, divided by a1. So although we have to double the p to get the same delta L1, so twice delta L2 of strain, the fact that we are dividing it by the area and the area is twice as much brings this this quantity, this property of this sample here back in line, such that we can plot stress on this line against strain and then have a line which is relevant to all samples regardless of their cross-sectional area and regardless of their original length. So that is why we use these variables, or these quantities, these characteristics of the sample, stress and strain, instead of what we originally looked at, which seemed an intuitive way of looking at it, the force that we applied compared to the change in length. And the reason we've done that is so that we can look at a value which allows us to compare all samples regardless of their original length and regardless of their original cross-sectional area. Okay.